new chapter today. And if you're watching this at home, that means you weren't in class in person, but I hope this makes um, for a somewhat decent substitute of being here in person, this recording. I've got some warm-up questions on the screen for us to start with. So I'd like for you guys, as you've got your notes out, to consider what is going on with each of these operations. In chapter 10, we're going to study a lot about functions. You may or may not remember how functions work. Functions are relationships between sets of information, sets of data. We call the set of inputs the domain. What do we call our set of outputs? Very good, the range. And so really, these two functions, what we're checking here with this warm-up is to see, do you know how to add and subtract and multiply polynomials? That's all it's checking, okay? So like, for example, before we get into it too much, George, what kind of function is f of x? What kind of polynomial is that? Classified, it's in this form. Instead of f of x, if I wrote it up as y, we've seen a type of function this year quite a bit. Okay, good. So that generally speaking, that's a linear function. Now, George went above and beyond and said it's in slope-intercept form. So, Stephen, you could probably tell us a little bit about that line, right? What would you tell us, given that it's huh? And it's very good. So it's y-intercept being 5, its slope being 1. Fabulous. So we know a little bit about f. Okay, not that that's going to help us with these examples, but okay. So if I were to look at the g of x function and write it up instead of g of x, write it up in y equals form, it's not linear, is it, Nicholas? What kind of function is it? Very good. It's quadratic. And Cole, could you tell me, is this well, first of all, what's the shape of a quadratic function called?
A parabola.
Good. And is it concave up or concave down?
Concave up.
Very good. Concave up. And Ryan, what will be the y-intercept of that parabola? Remember, your y-intercept is always where x equals 0. And if x equals 0, what would y equal? I'm literally covering up these terms, so you just read y equals 8. Right, so our cover-up principle is when we plug in x equals 0, cover up all of those terms that have x in them. All right, so we could glean a little bit about each of these functions. That's just kind of icing on the cake since y'all got exams coming up. Some good review about linear quadratic functions. But what I want us to do here with example 1, 2, 3, and 4, and I'll shut up and get out of the way, is to add these two functions together. So in other words, you're going to take and you're going to add these two highlighted polynomial expressions. That's all you got to do. Add them up. And then subtract them in a different order, and then on number 4, multiply them together. So that's all we got to do here. Y'all get to work. I'll give you a few minutes to think about this. And again, chapter 10, which we're starting today, is all about operating with functions. So this will be a good, appropriate warm-up for us. Fill up some water. I'll be right back. I'm getting a message. Oh, transcription has started. Look at that. And then that's all you got. There's no equal. But it's new work thinking with it, so that's your answer for your question. And then you'll do the same thing just with subtraction on the second one. By the way, if I'm subtracting, this is a good time to break this up since most everybody's at I think number 2 and number 3 by now. If I'm subtracting a polynomial, what do I have to remember to do? I know it's a vague sort of question, but like if I said, "Dad, Gummit, Patrick, I'm sick of your road, just get out." You know, that old shtick, right? When you're subtracting a group, what do you have to do? Just the first term, you think? Ah, there we go. That's good. So like if I was going to subtract f minus g, that's a binomial minus a trinomial. So in other words, that's my first 2 terms minus those other 3 terms. I like how Nicholas said, hey, you gotta subtract or change the sign of each of those terms. I like to put parentheses around it so it reminds me what property does that illustrate. Not associative. Look, that minus sign being applied to. Yeah, that's your distributive property in disguise. So like if I'm subtracting Patrick's row, I'm going to subtract Patrick and Stephen. I'm not just going to subtract that first term. It's a real common mistake. A lot of times I'll see students, they change the sign of that first term, and then they're like, minus 4x plus 8, and then they're done. Whereas we want to change the sign of all 3 of those terms. And then conversely, on number 3, when you guys set that up, it's x squared minus 4x plus 8. We're not changing the signs of that trinomial. Because we reversed the order of the subtraction, we're going to change the sign of the terms in that binomial. So it's going to become minus x and minus 5, which, you know, again, isn't super challenging. We just got to make sure we set it up properly. All right, so we got x plus 5 plus x squared minus 4x plus 8. All right, Ryan, what do we get on number 1 as a result? Did you say plus 13? All right, very nice. Okay. Now, as I was walking around, I noticed like the temptation is to say, oh, I got to solve that now. And think, 13, I got to use my quadratic. Remember, it's not we're not solving any kind of equation. All we're doing is just figuring out what does that expression equal. It's in its most simplified format. All right, Nicholas, you were talking to me about changing the sign of each of those terms. So what'd you get in number 2? Speak up. Oh, f of x minus g of x. And I didn't say it with number 1. I should have, and I'll certainly say it with number 2. I like how both of these guys gave me their answer in a nice, neat format. They gave me the x squared term first, and then the x term, and then the constant term. Even though stuff might be shuffled around, always putting our answer in that general or standard form is pretty smart, pretty good. Now, with this next 2, I like, again, how we distribute the negatives. This is going to become negative x. This is going to become negative 5. So, Cole, what do I get when I put those 2 together?
X squared minus 5x. Minus 3.
Try again. What's 8 minus 5?
3 plus 3.
There you go, plus 3. Now, let me ask you a quick question here. Patrick, you feel like doing a little arithmetic for me? I'm gonna ask you some tough arithmetic. Here we go. Hey, Patrick, what is 7 minus 5? Okay, here's a follow-up question. What's 5 minus 7? Negative 2. Interesting. What's the relationship between 5 minus 7 and 7 minus 5? I want a vocabulary word. They are opposites. They are opposites. All right, now this is something sort of innocently hiding in the background here, but if I've got A plus B and A minus B, we've learned those are not opposites, those are
Conjugate.
good. Those are conjugates. And I kind of harped on you guys earlier when we were studying about a binomial and its conjugate and how we don't want to confuse it with the quote opposite because, right, the opposite, A minus B, the opposite of that would be B minus A. Those are opposites. Okay. And so if you notice here, we've got over on the left, we've got F minus G in number 2, and then we got G minus F in number 3. Those are opposite. And so I think, yeah, Cole, I was asking Cole what he got when he combined all of these terms over here. And actually, I was kind of cheating. I was just, as he was giving me his answer, I was checking to make sure it was the opposite of what we just got in the previous line. You know what I mean? And that can be a little bit easier. I can save you the work of thinking, oh, well, I just did F minus G. Now he wants G minus F. Well, I'll just take the opposite of my answer that I had from the previous one. And if your answer is sound on the previous one, then of course it's going to be sound on that next one. Questions or comments about that, Patrick? Go for it. All right, so this minus sign being distributed, it is as though we are saying x plus 5 minus x squared minus negative 4x minus 8. And then we would simplify that out and kind of shuffle some things around. So like, for example, that the only quadratic term we had was negative x squared. So he's done. And then I've got a couple of linear terms. I've got a plus x and a plus 4x. So that made for plus 5x. And then over here, once those were out of the way, we had a 5 and a negative 8, and that made for a negative 3. Okay. And so the idea of subtracting a negative, we changed the sign to a positive, and then we just lined up our terms there. And it would work similarly for number 3. All right. Now, we get to number 4, and we maybe have a little bit more work to do. I don't know. What's up? What is number 4 as far as process goes? What does it remind you of that we've learned about a lot this year? Very good. That idea of multiplying polynomials, our acronym FOIL oftentimes comes up. Stephen, when do I do a FOIL technically? Correct. When you're multiplying a by times a by, we do first, outer, inner, last, and we get 4 terms, and then sometimes they simplify them, like we might combine them and get 3 terms, get like a trinomial as a result. Is this technically a FOIL problem? What do y'all think? Is this a binomial times a binomial? No. But we could sort of mimic the FOIL process. Let me write this up. And did y'all have a chance to get this one? All right, one little more time while we're thinking about it. Well, and I'll kind of set the table for you. And you guys can kind of tell me if a by times a by in FOIL, FOIL, 2 terms times 2 terms generates 4 terms. What do you think a by times a try is going to yield? How many terms? It's going to give us 6 terms before simplifying. So technically, we don't have a nifty little acronym like FOIL, but we can mimic that process. We could do, and here I'll kind of color code it, we could do x times all 3 of them, and then we could come back and say 5 times all 3 of them. Okay. George, give me the red ones. What do we get when we dump x into that trinomial? All right. And then Ryan, what do I get when I multiply the 5 into them? Right. And so now, by the way, do y'all notice how I kind of lined up our like terms from what George and Ryan gave us? Those like terms, I just kind of lined them up. And now we can combine them. Steve-O, what do we get?
Minus 12x plus 40.
Perfect, 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 perfect. And multiplying polynomials like that, really, it's not a super complicated skill. you just got to keep your head on straight and don't get distracted and don't slip up on little careless arithmetic mistakes. You know what I'm saying? Okay. So technically, I could give you guys a trinomial times a trinomial. How many terms would that yield? 9 terms. And then you'd simplify it all down, and it would be a pain in the booty. In algebra 2, a lot of times what you do things like this. You take, we'll just do like x plus 3, and you raise it to a particular power, right? And then there's a lot of that multiplication. Now, you might say, well, Coach Morgan, what? Well, that's not hard. That's just x to the 4th plus 81. Wrong. What's x plus 3 to the 4th power? The same thing as saying x plus 3 times x plus 3 times x plus 3. You get what I'm saying? This is called binomial expansion, by the way. You'll learn it in algebra 2, x plus 3. And then maybe you FOIL these two guys and you FOIL these two guys. X squared plus 6x plus 9. Right? And then you wind up getting, let me see if I can do this in my head here. H to the 4th, x third, x squared, x 3, 9, 27, 81. You get something like this. Now, I know the shortcut that you learn in algebra 2. You guys, the point of today's lesson isn't to do that. But good golly, Miss Molly, there's a lot of room for error in there. Like we said, a try times a try would give you 9 terms, and then those 9 terms would combine together. And so stuff like that, you just got to, like I said, keep your head on straight. Don't make any careless mistakes, and show a lot of work. Show your steps. Okay. You have any questions or comments about the warm up? Feel free. Nada. All right. What's the one operation we haven't done yet? We haven't done division yet. We did add, subtract, and multiply. So let's look at a division problem. Let's scroll that down. All right. So here we're given f of x and g of x again. Okay. Patrick, what kind of function is f of x?
Quadratic.
Good. Stephen, what kind of function is g of x? Quadratic. Good. We got quadratic over quadratic. That's what we're looking for. Now, check this out. If we're given those two functions in red, and then they ask us for, all right, they say, hey, we want f over g of x, also known as f of x over g of x. I hope that you understand this is a division problem. Okay. And so there's 2 ways for us to look at this division problem. One way that you guys have learned it already is just to set one on top of the other. And to look at it as a rational expression. How do I simplify, Nicholas, how do I simplify rational expressions like this? Very good. Everybody hear that? You would factor the top and the bottom and see if anything canceled. Now, what's the drawback of that? Does everything always factor every time? No, and certainly everything doesn't always cancel all the time. So if we're lucky, now I've made this first example such that it will factor. If we're lucky, it factors and cancels. Okay, so Ryan, factor the top. And let's see here. Patrick, factor the bottom. I've only got 60 y'all in here, so y'all getting lots of questions. Ryan, holler at me whenever you got the top factored. And Patrick, the bottom. Beautiful. That's a good refresher for us. Again, kind of thinking of the exam prep, factoring. We learned a boatload of factoring techniques. Ryan did just a regular trinomial, looking for 2 factors of the constant term that add up to the linear coefficient. And then Patrick did the difference of 2 squares. Beautiful. And then I hope it's obvious, Cole, at this point, what cancels?
X minus 7, X minus 7.
X minus 7 cancels out. So this simplifies down to x plus 1 over x plus 7. There need to be some restrictions. George, can you list one restriction? What should x not equal? Ooh, you got them both. That boy. Plus or minus 7. And just as a reminder, the restrictions, they don't come from the end. Like the rookie would say, the rookie mistake would be to say, x can't equal -7. But look at the original problem. The original problem had a quadratic denominator, so there were 2 roots. Okay. All right, so Can I cancel the X's out on my final answer over here? Can I scratch those two X's out? Why not? Plus sign, roadblock. All right, those terms, we don't cancel terms. We only cancel common factors. That's the same reason why we wouldn't scratch out X squared at the very beginning and say, oh, there's X squared on top and bottom. Well, so what? They're terms. You can't cancel. Okay. Now, everybody in here should be pretty doggone comfy with working the problem that way. Okay. But as we said, the drawback is that not everything always factors, not everything always cancels out. And so I want to consider an alternative approach. Does anybody remember how else we've done a division problem like this? One polynomial divided by another. Long division. Mr. Hedrick came to play ball today. I love it. So let's practice doing some polynomial long division. This has come up just in the last week. As a matter of fact, this has come up twice in our calculus class, my honors calculus class for seniors. And so it's a skill that we use all throughout high school. So which one's the dividend? Which one's the one that goes like, quote, in the house? Yeah, our numerator. And then going on the outside would be our divisor. Cole, do you notice anything interesting about how I wrote up our divisor?
You added in 0.
Anybody tell me why I added that 0, Steve?
I have to write them all the same.
Yeah, we don't want to skip any terms. Now, technically, you could work the problem. It's doable without putting in the 0 placeholder. But why would you want to make it way more difficult on yourself, right? We talk about taking steps, best practices to eliminate careless mistakes. That's a great best practice. It's easy to employ. You literally just put the 0 placeholder in, and now everything's going to be lined up. Why don't y'all take a stab at that one on your own? Why don't you walk through? I've already taught you how long division works. See if you can remember doing it. Have y'all done polynomial long division in y'all's classes yet? Last week? Okay, cool. So y'all should be somewhat familiar with it, you guys from PORO. And then OLPH, y'all haven't got there yet? You can say like, so, oh, okay, I'm playing catch up, sorry. So like, after you put your one there, write those 3 under there and change that to something to subtraction. It will be linear, and it won't have to be another. So. Let's see. I haven't done it yet, and I can't remember. Can everybody agree that 1 is the term in my quotient? Number 1, and we get x squared, 0x, and negative 49. Okay, Ryan, after I've multiplied, what do I do? Good, we're going to subtract. Now, what that means for me, changing the signs, that first term cancels out by design. We get negative 6x. George, what was it that you had said? Is it 42? It's supposed to be 42, I think. Negative 6x plus 42. All right. And I'm going to stop there. That's my quote remainder. Okay. Because once I get down here and I've got something that is of less degree than the divisor, that's when I stop. I throw on the brakes and say, all right, we're good for there. So look at how I'm going to write my answer up here. My quotient is 1 plus negative 6x plus 42 over x squared minus 49. All right. Now, that's not going to be my final answer because it needs to be simplified a little bit. Okay. So again, let's make sure we understand our division algorithm. We've got the dividend over divisor equals quotient plus remainder over divisor. That's exactly what we've just done. We've gone 1 plus this or that. Not to talk down to you guys, but it's like if I were doing a division of 7 divided by 5, I'd say that's 1 with a remainder of 2, right? How would I write my answer up? I'd say 7/5 equals 1 plus 2/5, or 1 2/5. That's precisely what we've just done here. It's quotient plus remainder over divisor. But what could you do with your remainder and your divisor in blue there? Did anybody notice you could what? Absolutely. We're going to simplify. Okay, so what does that mean? That means I need to take out a -6 and be left with x minus 7. And then down here, just like we did a moment ago, x plus 7, x minus 7. And we would cancel out the -7s. So my final answer here is going to be 1 minus 6 over x plus 7. And then with the caveat that x cannot equal plus or -7. Same reasoning behind my earlier restrictions. Now, that's 2 ways of working the same problem, and y'all notice we got two answers that look a little different. Okay, 2 answers that look a little different. Fellas, this is the equivalent. Y'all saw the elementary school example that I put up in red. Right. Yesterday, one of my children was doing some math. Right, they got TCAP this week. Right, y'all. Anybody ever do TCAP? Did y'all grow up going to public school at all? So TCAP is Tennessee Comprehensive Assessment Program, and it's like the standardized testing for elementary schools. And so, anywho, my kids have that this week and next week, so it's a big deal at public schools. And so I was helping one of them with last night with some fraction action, and it was like solve the equation W plus some fraction equals some other mixed number. And the trick was turn both of them into improper fractions, combine, and so on and so forth. Our 2 answers right here, like the problem we were working last night, we got our answer as an improper fraction. That's like my first answer. Okay, just a fraction was the answer. But those weren't any of the choices. They had to take it and turn it into a mixed number. Our second answer is like a mixed number. Second answer is like a mixed number. If you wanted the second answer down here to look like the first answer, all you have to do is change this 1 to a x plus 7 over x plus 7. Combine the 2 fractions, and you get what you had up there. You know what I mean? So like literally, if you changed this 1 to an x plus 7 over x plus 7, and then you combined these numerators, what's x plus 7 minus 6? And that's exactly what you had over there. Divide by x plus 7. Okay, so it's just when you do a problem with a different technique, like we did polynomial long division as opposed to factor and cancel, your answer is going to be mathematically equivalent, but sometimes it's going to be in a different format. Okay. Is that ringing a bell for us as far as warming up and practicing and reviewing goes?
The first answer, is it the equal sign for the x equals plus minus?
Oh, it could be not equals. Is that what you meant? Right there? Oh, I messed up. Silly me. Is that what you're asking though? Okay, I jumped the gun when you started talking. I saw that equals sign should be a not equals. And I said, I think that's what he's asking about. Anybody else? Awesome. Okay, so everything we've done so far, example 1 and our 3 or 4 warm-ups, it's a good exam review. The exam for you guys is coming up. And so you want to be cycling back through some of those things that you maybe haven't covered in a while. Definitely want to be good at factoring. Definitely want to be good at division, like long division and things like that. What we're going to move into now is so again some exam review, but maybe it's a little bit more difficult. All right, this is going to be where we've talked about the composition of 2 functions or composite functions. Sometimes I'd say. Okay. The other night, Friday night, I made some burgers at home. Okay, you guys ever make burgers? Making burgers? Nobody in here likes to make burgers, huh? You like burgers? So I tried a new burger recipe. Okay, I got some ground beef and I got some onions and I got a bunch of seasonings, some sesame seeds and some other things, and poured it all in my bowl, and I just got down there and just mixed it all. It's kind of grody doing that, but mixed all the meat together with all the onions and all the whatever. And then I made my patties. Okay. And then what I like to do, you know how you make a burger, you put cheese on top? cheeseburger, right? Everybody does that. Well, what I like to do is I like to put the cheese inside the burger. Okay, you ever do that? It's like the stuffed crust pizza idea. Okay, so like you take your patty and then you put some cheese and you put another patty on top of it and you kind of make it to where the cheese is up inside the burger patty. And then when you cook it, what happens to the cheese? Oh, it melts. It gets all ooey and gooey and delicious. All right, that is sort of the culinary equivalent of what we're doing here. We are taking a function and we are putting another function inside it. So you got the outer function that in my little cooking analogy is like the burger meat, and then you got the inner function that's sort of like my cheese. Okay, and that's what we're looking at here. In this first example, f of g of x, f is my outer function. That's the burger. G is my cheese. G is on the inside. So our normal f rule right up here would say, all right, take whatever's in parentheses and add 5 and take the square root. Okay, like for example, George, what is f of 4? Plug 4 in and what do you get? So you end up with 3. Very good. So 4 plus 5 is 9. Square root of 9 is 3. So f of 4, we literally get by saying plug in 4. And, we get out whatever we get out. Okay. Cole, what would f of 11 yield? Yeah, very nice. We'd get 4. Again, because what did he do? He plugged in 11 plus 5, so on and so forth. Okay, Stephen, what would f of, I'm going to ask you a little bit of a weirder one, okay? You ready? What would f of triangle yield? Could you do anything with it? No, man, it's just square root of triangle plus 5. Coach Morgan, you can't do anything with it. Like earlier, I gave George a number that would add to 5. I gave Ryan a number that would add to 5. Okay, triangle, well, I don't know what the dumb triangle is, so it's just, it is what it is. Okay, let's do f of, we'll do f of coal. Okay, what's that going to yield, class? Yeah, square root of coal plus 5. Okay, so you get the idea. The rule says whatever's in the parentheses, add 5 and take the square root. So when I see f of g, I'm going to say square root of g plus 5. That function g gets inserted into the function f. Now, do we know what g is? Do we know what g is? Everybody nod their head. Yes, it's been defined as what? 3 over x. So we're just going to do 3 over x plus 5. Now, much like Stephen's triangle plus 5 or coal plus 5, 3 over x plus 5, they're not going to combine. Now, I guess you could get like terms, but that would be going above and beyond. We just leave it as 3 over x plus 5. You put one function inside of another function. Let's see if we can do it in reverse. The G rule, I'll change color here. The G rule says we're going to do 3 divided by whatever. So if I said G of 7, it would be 3 over 7. G of 10, it would be 3 over 10. G of Nicholas, it will be 3 over Nicholas. G of spaghetti, it would be 3 over spaghetti. The rule says G of whatever is, in this particular example, means divide 3 by whatever. So G of F means 3 divided by F. And do we know what F happens to be in this example? You're daggone right we do. F is what? Square root of x plus 5. So there's our composite function. Okay. You have just put the cheese in the burger. Very nice. As far as notation goes, up here in parentheses, I've got a note. I hope you wrote that down. That you see F-O-G, F and then a little bitty O and then G, or G and a little bitty O and then F. That's an older notation, a little bit more antiquated. F-O-G. It's the same thing as is F of G of X. Okay, so just make mention of that in your notes, because sometimes you'll see that either Delta Math or in a textbook, F-O-G or G-O-F. That just means, well, nobody goes golfing in the fog. And so I would look at it instead as like F of G, where the function is positioned actually inside the parentheses. Okay. Now, I'm going to leave you with another culinary analogy. Okay. But I got to look it up and show you a picture though, because you're not going to believe it. You just won't believe it. There's a thing called a turducken. Okay. Anybody ever heard of a turducken? Have we talked about the turducken in here? The turducken is a creation of John Madden's. At least he made it popular one Thanksgiving football game. It is a chicken shoved into a duck, which is then shoved into a turkey. And then it is cooked and made delicious. So like this one was a somewhat interesting look because they had put other stuff in besides the birds. So this one they had put looked like some cornbread dressing inside the chicken, and then they shoved that in. Duck is dark meat, and then they shoved all of that up inside of a nice big turkey breast, and so it's called a turducken. Okay, so Nicholas, have you all ever done a turducken? No? I have not been bold enough to try it, but it seems like it would be very interesting. My friends, I'll leave you with the turducken in math. Okay, what is it? It's the same analogy that I gave with the burger and the cheese, except in this case, there's three things. All right, there's three functions. You've got H, which is our little cute little chicken. He's all the way on the inside, and he has been shoved into G, the duck, and that has been shoved into F, the turkey. Okay, so we'll pick up with this tomorrow, but what we've got here is the exact same process. You just put one inside the other, and see what shakes out. Okay, we'll pick up with this tomorrow. You guys can go ahead and skedaddle. Those of you that are watching at home, I'll have another video for tomorrow. So thank you for listening, and live Jesus in our hearts forever.